The tank sat on its transport trailer at the Aberdeen Proving Ground in Maryland in the autumn of 1942, still carrying the grime of the assembly line. It was not a beautiful machine. It was tall for a medium tank, taller than the Germans preferred, with a boxy hull and a rounded turret that looked, to some observers, more like a piece of farm machinery than a weapon of war. The Continental radial engine at its rear had been borrowed almost directly from aircraft design. The suspension ran on vertical volute springs, a system developed for light tanks on flat American roads rather than for the shattered terrain of North Africa or the river mud of France. The 75mm gun in the mantlet was adequate against the armored vehicles Germany had been fielding through 1942. It was not adequate against what Germany was building for the years to come. The men at the armored board who walked around that vehicle that autumn were not, for the most part, worried. The tank met the specifications the War Department had issued. It was faster than what it was replacing. It was simpler to manufacture, simpler to repair, simpler to supply. At a moment when the industrial machinery of the United States was still finding its pace, simplicity was not a secondary virtue. It was the primary one. They signed off on it. Production began in earnest. The Lima Locomotive Works in Ohio sent the first M4A1S down the line in February of 1942, and within months the machines were moving through the Atlantic and into the hands of the Eighth Army in Egypt, where they would fight their first major action at El Alamein that October. What nobody at Aberdeen that autumn had fully accounted for was the gap between what the tank was and what it would need to become. The Germans were not standing still. The Panzer IV was already receiving the long-barreled 75mm gun that would make it genuinely dangerous at combat ranges. The Panther was being drawn on drafting tables in Munich, a direct answer to the Soviet T-34, 60 tons of sloped armor, and a high-velocity gun that would arrive at Kursk in the summer of 1943 and announce itself in the worst possible way. The Tiger had been in the field since Tunisia, and the American Army, committed now to a war it had been slow to enter, was discovering that the machine it had sent to do the fighting was falling behind the threat it was being asked to defeat. If this story is pulling you in, take a second to hit the like button and subscribe, and drop a comment telling me where in the world you're watching from. It means a great deal to know who's listening. What followed between 1942 and the end of the war in Europe was not a single stroke of inspiration. It was a systematic program of engineering corrections, each one driven by a specific failure that had been documented in the field, each one contested by the institutional inertia of an army that did not always recognize a problem until the men who were dying from it put it into writing. The story of how the Sherman was made to fight the war it actually found, rather than the war it had been designed for, is the story of how an industrial democracy goes about correcting its own mistakes under fire. It is not a glamorous story. The names attached to it are mostly in the technical manuals, not the after-action reports. But the decisions made in the ordnance laboratories and on the testing ranges, the choices about suspension geometry and ammunition stowage and gun caliber and engine configuration, were as consequential to the men who climbed into those vehicles as any tactical decision made at Army group level. The first failure was fire. At El Alamein, and in the fighting across Tunisia through the spring of 1943, Sherman crews and their British counterparts began reporting something that the manufacturers had not fully anticipated. When a German anti-tank round penetrated the hull, the tank burned. Not always, not inevitably, but at a rate that the Army's own post-war studies would eventually quantify at somewhere between 60 and 80% of vehicles that took a penetrating hit. The ammunition was stored in bins along the sides of the hull, upright in the sponsons, positioned where they were accessible, but where they were also directly in the path of a projectile entering from the flanks. When a round punched through and struck a propellant charge, the result was immediate and catastrophic. British crews gave the tank a name it would carry for the rest of the war. The Germans called it the Tommy Cooker. The Americans heard the same stories and called it the Ronson, after the cigarette lighter whose advertising slogan promised it lit every time. The Ordnance Department studied the burn reports and traced the problem to the propellant stowage. The fix, when it came, was elegant in the way that good engineering solutions often are, not a redesign of the ammunition itself, but a redesign of where it lived inside the tank. By late 1943, the solution being tested was wet stowage. The ammunition bins were relocated lower in the hull, down to the floor of the fighting compartment, and the bins themselves were double-walled, the space between the walls filled with a mixture of water and ethylene glycol. The principle was straightforward. If an anti-tank round penetrated the bin, the liquid would flood the breach point before the propellant could ignite. Army studies conducted after the modification entered production showed that wet stowage reduced the fire rate to between 10 and 15% of penetrated vehicles. The same hit that had been killing crews in Tunisia now, much of the time, simply punched a hole in a tank that kept fighting. Production of the first wet stowage variants, the M4A3 with the designation W added to its suffix, began phasing in through the early months of 1944. The modification was not announced with ceremony. It appeared in the production sequence as an engineering change, one item in a long list of incremental corrections that were quietly accumulating across every variant of the design. The tankers who received the new vehicles did not always know exactly what had changed. What they knew, eventually, was that the burn rate was different, that the men who took a hit had a better chance of getting out than they had before. The second failure was ground pressure. The Sherman's original vertical volute spring suspension ran on tracks 16.5 inches wide. That was sufficient for the roads and proved ground of a proving range in Maryland. It was not sufficient for the mud of Normandy, for the soft delta soil of the Po Valley, for the snow-covered lowlands of the Rhineland in winter. The narrow tracks concentrated the vehicle's weight onto a small contact area, and in soft terrain the tanks bogged. The Tiger, with its broad tracks, did not bog as readily. The Panther, whatever its mechanical difficulties, sat lower on wet ground and moved across it with less resistance. The engineering answer was already being developed before the Normandy landing. Work on a horizontal volute spring suspension, a redesign that laid the spring on its side rather than standing it upright and allowed the use of much wider tracks, had been underway at the Armored Board since 1943. The new system, designated HVSS in the technical documents, doubled the number of road wheels per bogie from 2 to 4, which distributed the vehicle's load more evenly and reduced the shock transmitted to the crew over rough ground. The tracks it used were 23 inches wide, 40% broader than the original. Ground pressure dropped by roughly a third. The vehicle that had been outperformed in soft terrain by its German counterparts could now go where they went. The first production Shermans fitted with the horizontal volute spring suspension reached the European theater in December of 1944. By 1945, they were arriving in sufficient numbers that armored commanders were making specific requests for them when replacement vehicles were allocated. The tank crews who received the HVSS vehicles noticed the difference immediately. The ride was smoother. Crew fatigue dropped over long movements. The tracks held in mud that had stopped the older suspension cold. The variant equipped with both the new suspension and the 23-inch tracks acquired, through the designation system, the phonetic nickname that would follow it out of the war and into the histories. The E8 prototype designation, applied to the horizontal volute spring suspension package, became Easy 8 in the mouths of the men who drove it. The nickname stuck because it was earned. This was a different machine from the one that had reached North Africa in 1942, and the men inside it knew it. The third failure was firepower. It was the most contested, the most politically complicated, and the last to be resolved. The 75mm M3 gun that the original Sherman carried was an adequate weapon against the Panzer III and early Panzer IV. Against the long-barreled Panzer IV, it was marginal. Against the Panther it was, at standard combat ranges, largely useless. The frontal armor of the Panther ran to 80mm of sloped steel. The 75mm shell, firing at standard combat distances, could not reliably penetrate it. The Tiger's frontal armor was heavier still, and its 88mm gun could kill a Sherman at ranges where the American tank's own rounds fell away without effect. The Ordnance Department had not been asleep. The 76mm M1 gun had been under development since 1942, and a mounting that would fit the M4's hull had been worked out by August of 1943, using the larger turret ring from the aborted T-23 tank program. The new gun threw a heavier projectile at a significantly higher muzzle velocity. It could penetrate the Tiger's frontal armor at reasonable combat ranges. The Army ground forces had been offered it. They had declined. The reasoning was not irrational, only wrong. The 75mm gun carried a more effective high-explosive round, useful against infantry, field fortifications, and unarmored vehicles. In 1943, with no direct combat experience of the Panther and a limited exposure to the Tiger, the Army ground forces calculated that the majority of tank engagements would not be against heavy German armor. They were correct about the arithmetic. The majority of engagements were not against Panthers and Tigers. What they misjudged was the cost of the minority that were. When the armored columns of the First Army pushed inland from the Normandy beaches in July of 1944 and encountered Panther tanks in the bocage at ranges of a few hundred yards, the 75mm gun gave the crew an unpleasant education in the difference between a weapon that was usually adequate and a weapon that was adequate when it mattered. General Dwight Eisenhower, in a communication to the Ordnance Department in July of 1944, recorded his frustration in plain terms. He had been told by Ordnance that the 76mm gun would deal with anything the Germans had. He had now discovered that it could not reliably knock out a Panther from the front. The 76mm Shermans that had been sitting in England, held back because field commanders had been slow to want them, were suddenly very wanted indeed. General Omar Bradley of the First Army put in a request for every 76mm vehicle that could be sent to France in time for Operation Cobra. 102 M4 A1 variants armed with a 76mm gun arrived before the operation opened on the 25th of July, 1944, and fought their combat debut in the breakout across the same basin. If this is the kind of history you want more of, subscribe and turn on notifications. There is far more in the record still to cover. Your support is what keeps these stories coming. The introduction of the 76mm gun did not solve every problem. The gun's early muzzle blast obscured the target, making it difficult for the gunner to observe where the shot had struck and correct his aim. The high explosive round was less effective than the 75mm equivalent. And even after tests had suggested it was adequate against the Panther, field experience by the autumn of 1944 was producing a different verdict. Against the Panther's sloped frontal armor at standard engagement distances, the 76mm armor-piercing round still fell short. The Armored Board at the 12th Army Group conducted tests in January of 1945 and confirmed what tankers had been reporting for months. The 75mm gun could not defeat the Panther frontally. The 76mm gun could not defeat it reliably. The standard answer to a Panther, the answer that Patton's armor doctrine codified and that the veterans of the bocage had learned through experience, was to flank it, get to the side armor, get behind it, use the Sherman's faster turret traverse, its mechanical reliability, its numbers, and the ability of the crew to communicate over the radio net to close to an angle where the geometry favored them. There was a further dimension to the 76mm story that is easy to miss in accounts that focus only on the penetration tables. The gun was accurate, at ranges beyond 800 yards. Where the 75mm began losing coherence, the 76mm gun held its line. The muzzle brake fitted to later production versions of the M1 A2 reduced the dust and blast signature that had obscured the gunner's view after firing. High-velocity armor-piercing, discarding sabot rounds, developed late in the war, pushed the penetration figures higher still, and field reports from the last months of the European campaign described the 76mm gun on the M4 A3 hull as finally competitive at the ranges where armored engagements were actually being fought. The problem had been addressed. The addressing had taken 2 years and cost men their lives, but the record shows that the system corrected. The turret traverse was not incidental. The Sherman's power traverse allowed a well-trained crew to rotate the turret and lay the gun on a new target in seconds. The Panther's traverse was slower, and its crew had to balance a heavier turret on a steeper axis. In engagements where the ground was not flat and the ranges were short, the Sherman crew that moved first and acquired its target first had an advantage that the armor comparison charts did not capture. A post-war study by the Army's Ballistic Research Laboratory examined 30 armor-on-armor engagements fought by the 3rd and 4th Armored Divisions in 1944 and produced a figure that surprised many of the analysts who read it. Against the Panther, the Sherman had achieved a kill ratio of 3.5 to 1 in favor of the American vehicle. That figure needs context. It was drawn from a sample. It reflected the tactical skill of experienced American armored crews who had learned, through losses, how to fight their vehicle. It did not reflect the early months of the Normandy campaign, when the learning curve was being paid for in burned-out hulls. But it did reflect something real about what the late-war Sherman, the M4A3 with the 76mm gun, the Horizontal Volute Spring Suspension, and the wet stowage ammunition bins, had become by the last year of the conflict. It was not the best tank on the battlefield when measured by armor or by the brute penetrating power of its gun. It was something more useful, a tank that functioned, that could be repaired in the field with standard tools by the crew that had driven it, and that was available in numbers no German production line could approach. The production figures are the arithmetic of how the war was won. Between 1942 and the end of the war, American factories built approximately 49,000 M4 Shermans in all variants. The Chrysler Detroit Tank Arsenal alone, a facility that had not existed before the war and had been designed and built in less than a year, was producing tanks at a rate that German planners could not match with their entire armored program. At its peak, the Detroit Arsenal ran off more than 900 vehicles in a single month. The Panther, Germany's best tank, and the one most frequently cited as the Sherman superior, was built in a total of around 6,000 units across its entire production run. The Tiger I, the tank that had generated such fear in Tunisia, and whose name became synonymous in Allied accounts with everything dangerous and heavily armored, was built in fewer than 1,400 units across 3 years. The King Tiger, the heaviest production tank Germany ever fielded, reached fewer than 500. The German tanker who climbed into a Panther in the spring of 1945 was operating a machine that was, on paper, superior to the Sherman in frontal armor and gun penetration. He was also operating a machine that had an operational readiness rate, by the estimates compiled from German maintenance records, of roughly 50%. Half the Panthers assigned to a formation on any given day were in some stage of repair. The final drive, a component that German engineering corps reports cited repeatedly in the closing years of the war, failed under the stress of high-mileage movement at a rate that could leave a Panzer battalion stranded on a road before it reached the battlefield. The gearbox was better, and later production resolved some of the worst mechanical faults of the early OSD, but the fundamental design remained too complex for the supply situation Germany faced after Stalingrad. A precision-engineered machine demands precision-engineered spare parts, and precision-engineered spare parts demand a production infrastructure that was being systematically destroyed by strategic bombing through 1944. The Sherman's operational readiness, by the same measures, ran at 85% or better. When a unit moved, its tanks arrived. When a tank broke down, the repair crew could fix it with tools they carried, and parts were available because the same factories that made Shermans made the components to repair them, and those components fit every variant without modification. The Ford GAA V8 engine fitted to the M4A3 was the finest power plant installed in any Sherman variant. 450 horsepower, reliable, accessible from the rear deck, removable and replaceable in the field by a small maintenance crew in hours rather than days. The cooling system was efficient enough that crews operating in the Italian summer and the North African heat reported fewer overheating incidents than their counterparts in German tanks. The engine had been designed by Ford's own engineering department specifically for the M4A3, and the fact that a major automobile manufacturer had brought its production engineering culture to the problem showed in every aspect of how the power unit was assembled, serviced, and sustained across thousands of miles of operational use. The German tank crews who were captured and processed through Allied interrogation centers were, by the testimonies recorded in those reports, often more forthcoming about what the Sherman could do than their own command's intelligence assessments had been. They understood from fighting it that it was everywhere, that it kept coming, that a damaged one would be towed away and come back. What the Sherman could not do in a single engagement, the production system behind it corrected by attrition. There is an armor preserved in a museum in Ohio today. It is an M4A3E8, an EZ-8 with the Horizontal Volute Spring Suspension and the 76mm gun, the late war variant that incorporated almost everything the Ordnance Department had learned between 1942 and the final winter of the conflict. It sits on its wide tracks, 23 inches across, and the bogey wheels that carry are doubled up, the horizontal springs hidden inside the geometry of a suspension that was designed not in a single burst of inspiration, but through 3 years of incremental correction. The wet stowage bins are inside the hull, below the turret ring, surrounded by the glycol solution that nobody can see from the outside. The gun barrel is long and slender and accurate out to ranges where the original 75mm weapon had been marginal. The armor is not the heaviest armor on any tank that fought in Western Europe. The gun is not the most powerful. The vehicle is not the fastest. It is, taken together, a machine that could fight and be repaired and returned to the line and be supplied with ammunition and spare parts because an industrial economy had organized itself to produce it at a rate no opponent could match. The German engineers who examined captured Shermans in 1943 and 1944 wrote reports that acknowledged what they were looking at. The transmission was forward-mounted, bolted to the front hull plate, removable from outside the tank by a crew with basic tools. In a German workshop, the equivalent operation on a Panther required removing the tank from the field, moving it to a depot facility, and spending days on a repair that the American crew handled in hours. The German report noted this. It noted the reliability figures. It noted that the vehicle was designed to be maintained, not merely to perform. The conclusions in those reports were, in the language of military engineering documents, careful and restrained. What they pointed at was that the Americans had built something the German armor program, for all its technical sophistication, had not. They had built a tank for a war of attrition, and they had built it knowing that was the war they were going to fight. The story of the Easy 8 does not end with Germany's surrender. The tanks that came out of the Detroit Arsenal and the Fisher Grand Blanc plant in the last months of the war went on to fight in Korea, where the North Korean T-34s that crossed the 38th parallel in the summer of 1950 found their match. The Israeli Defense Forces ran modified Shermans into combat through the 1967 war and into the early 1970s, regunning them with French and then American weapons, adapting them to a doctrine of speed and aggression that would have surprised the men who designed them. One of those modified vehicles, an M51 with a French 105mm gun, destroyed Soviet-supplied T-54s in 1967. A tank that had been written off as inadequate in 1944 was still killing more recent designs a generation later, because the hull and suspension and drivetrain that had been progressively corrected between 1942 and 1945 had produced something that absorbed modification and adaptation in the way that good engineering always does. Look at that tank in Ohio again. Stand next to the wide tracks and the bogies and the long gun and the lower, more stable profile that the HVSS suspension made possible relative to the cramped original vertical volute layout. Understand that none of it arrived in the specifications as originally written. Every improvement came from a failure that had been documented in the field, processed through an ordnance system that was, for all its bureaucratic slowness, willing to change when the evidence required it. The fire rate that had killed men in Tunisia was answered with water and glycol around the ammunition bins. The ground pressure that had bogged tanks in the Normandy fields was answered with wider tracks on redesigned suspension arms. The gun that could not kill a Panther from the front was replaced, belatedly and under pressure from field commanders who had paid for the delay, by a longer barrel firing a heavier round at higher velocity. The men who made those corrections are not in the histories the way that the generals are. The ordnance officers at Aberdeen and the engineers at Detroit and the testing crews at Fort Knox who drove the prototypes until something broke and then drove the revision until it held are in the technical appendices and the development files. The tankers who climbed into the early M4S in Tunisia and found out about the fire problem in the worst possible way, and whose reports eventually produced the wet stowage modification, are in the casualty records. Their names are not on the tank in Ohio, but the tank in Ohio is the record they produced. Every engineering correction that runs through it from the first production Sherman to the Easy 8 of the last winter of the war is the accumulated answer to what they found and reported and died from, and sometimes survived. The German Panther was a better tank in the specific and narrow sense that its armor was thicker and its gun was more powerful. The late war Sherman was a better vehicle in the sense that mattered to an industrial war. It was available, it was reliable, it was reparable, and it kept improving because the system behind it was built to learn from its failures rather than defend them. By the spring of 1945, the Sherman that entered a Rhineland village was not the same machine that had landed in North Africa in the autumn of 1942. It carried the corrections of 3 years of combat documentation. The men inside had a better chance of surviving a penetrating hit. The tank had a better chance of crossing soft ground without bogging. The gun had a better chance of finding an angle that mattered. None of it was guaranteed. None of it was ever enough to make the mathematics of armored combat feel safe. But it was the difference between a tool that the war was trying to break and a tool that the war was making better. Thank you for staying with this until the end. If what you heard here stayed with you, the other films on your screen carry the story forward. Subscribe if you haven't, and I'll see you in the next one.